Let's discuss question number 11 from GATE 2011. So we are discussing GATE questions. GATE 2011. Let's discuss question number 11 from GATE 2011. So let me write down the question first. In a condenser of a power plant, the steam condenses at a temperature of 60 degree Celsius. The cooling water enters. So obviously you want to condense the steam, you need to provide a cooling medium, which is water here. The cooling water enters, that's what happens in a power plant, right? Enters at 30 degrees and leaves at 45. Now leaves at 45 degrees Celsius. The log mean temperature, or the logarithmic in full form, it's called logarithmic mean temperature difference, LMTD, of the condenser is, so there are four options for it: 16.2 degrees Celsius, 21.6 degrees Celsius, 30 degrees Celsius, and D 37.5 degrees Celsius. So let's solve it. So what is asked is LMTD, which is an important parameter in heat exchanger. So there are basically two methods in heat exchangers to solve a heat exchanger problem. One is the LMTD and the other is the NTU method. In the LMTD method, which is the first method, well, all the temperatures of the inlet and the outlets for both the fluids have to be given. That's what LMTD means. And so what is asked in this problem is, we are just asked to calculate the LMTD. Okay, so first let's draw the temperature versus the length. So for the hot fluid, the condenser and it enters at 60 and it only condenses. So during the phase change process of the steam, there is hardly any, there is no change in the temperature. That is the physics of the phase change. Okay, so this is how the hot fluid enters. Now the cold fluid enters, which is water, which enters at 30, and assuming that it's a parallel thing because nothing is specified, so, and exits at 45. Okay, so this is called delta T1, the temperature difference at the inlet. This is delta T2, the temperature difference at the outlet. So delta 1 T1 is 60 minus 30, which is 30, and delta T2 is 60 minus 45, 15. Okay, and LMTD, which is an important parameter in the calculation of overall heat transfer coefficient, that is defined as delta T1 minus delta T2 by log of ln of delta T1 by delta T2. So this is log to the base e. So delta T1 is 30 minus 15 delta T2, which we have just calculated, by ln. So I'm just writing ln is 30 by 15. So this turns out to be 15 by ln2, and if I use a calculator, this value comes out closer to 21.6 degree Celsius. So this is your LMTD. So let's look at the, I think option B is 21.6. So the option for this is, answer for this is B. Let's discuss another question from the GATE 2011, the question number 24, which is on heat conduction. So let's write down the question first. A pipe of 25 mm outer dia carries steam. The heat transfer coefficient, which is nothing but H, between the cylinder. So I'm writing the question because it will be useful. You need not have any other material in your hand. You can just look at this video and just concentrate on this video. And surroundings is 5 watt per meter square Kelvin. So this is heat transfer coefficient. So now what is proposed is, it is proposed to reduce the heat loss from the pipe by adding insulation. So you want to reduce the heat loss by adding insulation having a thermal conductivity of 0.05 watt per meter Kelvin. Okay, so which one of the following statement is true? Which one of the following statements are true? Okay, so we need to pick the statement which is true. So the outer radius of the pipe is equal to the critical radius, then the outer radius of the pipe is less than the critical radius. Adding the insulation will reduce the heat loss, and the last option is adding the insulation will increase. I'm just, in order to make it short, I'm just using shortcuts. Okay, so this is the question. So let's first write down what is you have a pipe which I'm assuming it is a cylindrical, so the outer radius is given, outer dia is given, which is 25 mm, so radius is 12.5 mm, half of it. Okay, and your heat transfer coefficient, which is the surroundings, so that is H, which is 5 watt per meter square Kelvin, and this is a solid pipe. So so you need to add now an insulation. Okay, so it is proposed that you have to add insulation which having a thermal conductivity K of 0.05 watt per meter Kelvin. So which one of the following statement is true? Okay, so already the radius is 12.5. okay, the outer dia, and now even if I add insulation, so how much, I mean whether it will increase or decrease my, okay, so let's say, I mean I've added insulation which is of very small thickness, I mean because the outer radius is almost 12.5, and I add a very small insulation such that there is not much change in the radius. So one thing which we know from the critical radius concept during the, I mean this is one of the important derivation which we do in heat transfer through radial heat transfer for cylinder. What we derive is the critical insulation for a cylindrical case is K by H, and what it means is, why we call it critical is that when we study the net heat transfer and how sensitive it is to the radius, the outer radius, we get a plot something like this. So this point is what is your critical radius, which is K by H. So if I have my insulation such that the outer radius of the composite thing, or the outer radius of the cylinder plus insulation, if the outer radius is more than RC, then adding insulation further will decrease the heat loss, and that is required. And if I'm on the left side of RC, adding insulation will just increase the heat loss, which I don't want. So now RC is derived from derivation by basically writing the conductive plus the convective part, and then just finding out when the Q is maximum, I get K by H. So let's calculate K by H. K is 0.05 thermal conductivity and H is 5. This is 0.01 meters, and in mm it is 10 mm. So for this combination of K and H, RC is 10 mm. So but already the pipe radius is 12.5, and even let's say a very small insulation would, so 12.5 is on the right side of RC, which is somewhere here. Okay, and if I add insulation, obviously it will go on the right side and it will reduce Q as per this graph. So adding insulation for this combination of K and H, adding insulation will be always right side of the critical radius, and hence it will always reduce the heat loss. So the answer for this is C. This is a very important, important concept in conduction. Okay, so you need to, so adding insulation will reduce the heat loss. Answer is C.